Okay. So so now at least we know that if I have common mode inputs, I can say that the circuit is symmetric, right? So now, earlier how did we find the small signal gain of the circuit? I mean, how did we actually compute the small signal gain of the circuit? Yeah, but V0 by V1 minus V2 is the gain, but what is the approach we took? How did we find? Short circuit GM and the output resistance. But let us say if this was a symmetric circuit like this, what would have been the approach you would have taken to simplify the calculation? The common mode and differential mode half circuit. So here we didn't venture into that approach because of this asymmetry. But now we just made the observation that when will this become symmetric? For common mode inputs, this is symmetric, right? So at least that part is clear. So at least if I decompose now as common mode and differential mode parts, at least for common mode circuit or for common mode inputs, this becomes simpler, right? So let's take a stab at it and try to find the response due to common mode and differential mode. Right? Again, only for common mode we can use symmetry, but let's do that and see. So again, I'm looking at common mode inputs, so which means both inputs have the same change VIC, right? So again, what can you say about the two currents? Same. So what can you say about the two voltages? Same. So whenever I see two voltages equal in this course, what will I be doing? I'll be shorting. So again, this reduces to the same old circuit. So this is 2x of M4. This is the IC. This is 2x of M2. And that's it. This is open. So what is the small signal V out now? If I make changes to the gate voltage, right, include R0 for all transistors, what might be the small signal change in V out? Yeah, why 0? Yeah, as he's pointing out, you see that at the bottom I have an open circuit, so which means I cannot have any current flowing here. So which means I cannot have any current flowing here. So which means if 0 current flows, the output is. So I mean, this is a trivial case, so let's make it interesting. So now again, why is this 0 now? The main point to notice, this became 0 because I had an open circuit here. And why is this an open circuit here? I had an ideal current source biasing this, right? But let's make it interesting. Let us say the current source is non-ideal, obviously. So it has some resistance, say Rx. Okay. So which means in the small signal picture, I'll have okay. So let us now try to find what is the small signal V out. So again, instead of doing all the KCL approach, let's try to find it using short circuit GM and RO. Okay. Again, for any linear network, I can model it as this Norton equivalent. So the output is the short circuit current, which is GM times the input voltage times R. Okay, this is V out. So I'm trying to find the short circuit GM. So try to argue with me. So let us say I'm shorting this. So first of all, tell me, I will have R0 for this transistor. What will be the effective R0 if I have two of them in parallel? I have R0 2 by 2, two of them in parallel. So I'll have R0 2 by 2, correct? And this, let me mark it here. I'll put it here. This is R0 2 by 2. So remember that this current and this current, what can you say about the two? Same, right? So let's try to find this current. So to find this current, what should I find first? Sorry, if I find this voltage, I'll know what is the current. So let's try to find this voltage, right? And when I short circuit the output, the R02, how is it coming with respect to Rx? In parallel with Rx. R02 is connected from this node to ground. So for this calculation, I will just assume that this is coming in parallel with Rx. Okay. So now tell me what is, if I call it Vx, what is Vx? If I were to redraw this, maybe I'll redraw this so that there is no confusion. So what I have is this. I have Rx parallel with R02 by 2, and this is short circuit, this is VIC, and this is Vx. I have redrawn the circuit for our short circuit GM calculation. Okay. So now tell me, I am applying the input at the gate, tapping the output from the source, and at the source I have some resistance, this Rx parallel R02 by 2. So what is Vx now? GM times that resistance by, yeah, so okay, let me write it, Rx parallel R02 by 2 by 1 plus GM times this. So this is, Vx is this factor times Vi. Okay. So now I have calculated Vx. So what is the current now? I call it Ix. Vx by Rx. So if I do this, okay, let me write it fully itself. Okay, sorry, I made a mistake here. See, I just wrote GM, right? How many transistors I have in here? So what will be the effective GM? 2 times GM. Single transistor will push in a current of GM VGS. I have 2 of them in parallel. So the total current is 2 GM times VGS. Okay, so the GM doubles. Okay, so this is 2 times GM of which transistor? M2. Okay, that's clear. That should be clear. So Ix is Vx by Rx. So okay, let me see if I can write it fully. This is 2 GM2 Rx parallel R02 by 2 by 1 plus 2 GM2 Rx parallel R02 by 2 by Rx. Okay. So okay, into VIC will be there, so I'll write this as GM. So this is my short circuit GM. Fine. So I found the short circuit GM. Let me erase all the other things. This is short circuit GM. So what is the other thing I have to find? So what is the resistance looking here? Again, what is the resistance looking up? Looking up, what do I have? 1 by 2 GM4. In parallel with, what is the resistance I have looking down? Remember, I have a transistor and some resistance connected at the source. So what configuration this is? It's again cascode. Approximately what is the resistance of the cascode? It is the intrinsic gain of this times the resistance. And what is the GM of this composite transistor? What is the R0 of this composite transistor? Intrinsic gain doesn't change. 2 GM R0 by 2. So this is parallel with GM2 R02 times Rx. This is approximate. So how can you further approximate this as? This is going to be much smaller than this fellow. So for all practical purposes, this is 2 GM. So the overall small signal Vout is this times the output resistance. So that's what we get done. I mean, we have calculated it. Let's try to see if it makes some sense. Let's do some sanity check. Okay. So what is one quick sanity check I can do here? Yeah, good. So if Rx tends to infinity, we know the result. What should that be? 0. If I tend Rx to infinity, what happens to this? I mean, here I have Rx directly. So if it tends to infinity, it is 0. So at least it makes sense. Okay. The way I calculated this, fine. If you have any doubts, get it clarified. Because this is what I would prefer doing instead of writing the entire KCL KVL. Right? This gives you some understanding of what each voltage and each current is. The only thing you have to remember are few results like what is the resistance looking into the this node, resistance of a cascode, and if I have, let us say, a common drain configuration like this, what is the output? Huh? Correct. Right. No, that's we did in the first class, right? I mean, not the first class. That's how we did in the initial, right? For that, we didn't assume anything. No. If you recollect the calculation we did for the entire short circuit GM, we did some reasonable assumptions that R0 is greater than 1 by GM. Yeah. Here also we are doing the same, right? Here also I am saying that if I have these two in parallel, I am ignoring the R0 component. Correct? Yeah, those are assumptions you do. I mean, if you don't make any assumptions, right? If I don't, approximate this as 1 by 2 GM4 and write it, it's going to be really long. I'm not gaining anything besides getting the accuracy of 4 decimal places or something. Right? That's not the point. Okay? That much is something you should do. Right? Okay, so now we saw for common mode. So what is the one other thing I should do? Differential mode. Let's do that. Oops. So one thing should be clear that only for common mode I can bring out the symmetry in the circuit. For differential mode it will not be. So you can't do any simplification. But let's just make some approximations to make our life simpler. So this is the same circuit. Incrementally the drain is short. I am looking at differential mode input V1 minus V2. So on one side I apply plus VID by 2, other side I apply minus VID by 2. Okay. Yeah, so here, I mean, let us say if this was a circuit like this, what would be your first, conclusion? Huh? Yeah, how will you make the circuit symmetric? Yeah, that is all the nodes along the line of symmetry is 0. Again, this we saw for any linear network. If you have symmetric linear networks like this, and if we have anti-symmetric excitation, by linearity and superposition, we can conclude that these two nodes will be 0. But right now we cannot say that because you have this asymmetry. Okay, but think of it like this. Let us say I now ignore the R0 for the NMOS transistors. That is, sorry. Oh, I am ignoring RXX for now. I mean, even if there was a resistance Rx, if this was symmetric, that node will still be 0. Right? That is completely from symmetry and linearity, and the fact that you are applying anti-symmetric inputs like this. Okay. For now, we will not include Rx because we already have one issue. You don't need to include too many problems at the same time. So now let us say I ignore R0 for the NMOS transistors, right? So think of it like this. If I have R0 for NMOS transistors, then whatever happens in these two nodes can affect here, right? And in this entire circuit, what is the asymmetry here? What is causing asymmetry? This, whatever is happening on the drain terminal is what is resulting in the asymmetry, right? And if I include R0 for the NMOS transistors, the effect of the drain voltages will impact this. Now let us say ignore R0, right? So which means whatever is happening here has no bearing on what happens here, right? Now if I just look at this portion of the circuit, is it symmetric or not symmetric? Okay. So if I ignore R0 of the transistors, then what can you say about Vx? Is the argument clear? I mean, you can work out using KCL. This will not be, like you can directly do it, right? You just have two currents. I mean, if you want, we can do that. But I mean, you take it as exercise and work out. This will be 0 if we have this. But the argument is this: we couldn't say this Vx to be 0 because of the asymmetry here, right? And only the R0 of the transistors were passing on the information of this asymmetry to this node Vx. If I ignore it, this guy will have no information of what's happening here. All it will see is VGS, that's it. Okay. Yeah, so in this case, Vx is 0, so then I can basically make simplifications. This basically becomes this. This is, let us say, plus VID by 2. This is grounded. Minus VID by 2. This is grounded. Okay. So now we can work out what is the small signal current here. GM1 VID by 2. What is the current in this direction? Same thing, GM1 VID by 2. Okay. So this current flows here. Sorry. The current through the PMOS transistor is same. That gets mirrored. So the total current is what? GM1 VID. So this flows through the output resistance. And what is the output resistance? If this was, I think, M4 and M2. What is the output resistance here? R04 parallel with R02. Is that clear? I mean, unlike the earlier case, there is no kind of coupling, right? Because whatever current flows, that flows to ground. This doesn't kind of go back. I mean, remember, here I have GM1 VID by 2 in this direction because I've applied a voltage here. It is not as though this current is kind of flowing back, right? So here the output resistance is just R0 of this in parallel to the R0 of this. So yeah, if I ignore R0 of this transistors, then you can do this and work. Okay. So cool. I'll stop here and we'll resume. So